May 20th is a day for the super nerds. I wasn't even aware of its significance until less than a week ago, and I imagine you're maybe in the same boat, so here's a brief history lesson. Feel free to skip it. I know this isn't a history podcast, but I kind of dig it. 145 years ago today, 17 nations signed the Meter Convention. At the time, in 1875, France owned both the official meter and the official kilogram. These are physical objects called standards, like a sphere and a bar that was a meter long, and the global community wanted a replacement for these and an organization to oversee the maintenance of these standards. France was still recovering from a rousing defeat in the Franco-Prussian War a few years prior, and they were keen to hand off the metric system to an international community instead of the Germans who had just given them a whooping. A few years later, in 1881, an attempt was made to define an electrical standard, starting with the ohm, where resistance was defined using a 1 square millimeter column of mercury at 0 degrees Celsius that was 104.9 centimeters long. This was bumped up to 106 centimeters a year later in 1882, and again bumped to 106.3 centimeters in 1892. These were known as the BA ohm for the British Academy, the legal ohm, and the international ohm, respectively. And both Kelvin and Tesla were actually in attendance at that last conference. You've probably heard of them. The change from 106 to 106.3 came because they discovered the standard they were using, wired coils, didn't quite match the mercury spec that they wanted to use, so they had to tack on another 0.3 centimeters to make the equations balance. The whole point I'm trying to make with this, though, is that on May 20th, a standard meter came to be, and from that we got the ohm, which was based on the meter. And that makes May 20th World Metrology Day. It just seemed fitting to bring in a couple folks who have known about this holiday a lot longer than me and who work with modern standards all the time, some of our Keysight Metrologists. I'd also like to thank the sponsor of this podcast, me. We just launched Keysight University, a free online test gear course system for engineers of all ability and experience levels. There are 30 minutes to an hour-long courses. They're all video-based, and I've learned a lot just putting them together. So if you like this podcast and our YouTube channel, you're going to love Keysight University. There's a link on the page, eestalktech.com, and in this video's description if you're watching the video version, or you can just go to learn.keysight.com. Go sign up for a course that sounds interesting. There's an RF power course, some oscilloscope probing courses, receiver testing courses, VNA stuff, and we're adding more courses all the time. Man, we have the best podcast sponsors. Anyways, let's get going.
Hi, I'm Bob Stern. I was the principal metrologist for Keysight Technologies for a number of years, and I have been heavily involved within CSL. I lead or co-lead the standards writing committee there that has been responsible for some of the Z540 series calibration standards. And I still participate in the International Laboratory Accreditation Cooperation, or so-called ILAC, who provides additional guidance documents to things like 17025.
Hi, I'm Chris Cox. I'm the regional metrologist for the Americas, covering North America, Canada, Brazil, Mexico. I deal with service delivery, so equipment coming out of our service centers, specifically related to calibration.
I'd like to make a quick apology from the editing bay. We had to revert to a cloud backup recording and we lost some audio. We're doing the best we can given the circumstances. We're all stuck at home. We don't have access to our normal gear, so thank you in advance for your patience. Now, when I was talking to our editor and I said, oh yeah, we're going to do a metrology podcast, he's like, okay, but why? And it's like, oh no, it's not meteorology, it's metrology. And even, in Microsoft Word, I was writing out like Metrologist, and it wasn't a recognized word in Outlook.
Yeah, they didn't like it.
So I always think of metrology as like the ultra geeks of the test and measurement and electrical engineering world. Like if you're into metrology, you're really into engineering and technology. For those of people who are less familiar with metrology and what it means and why it matters, how does it impact kind of on a global scale trade and the economy and how we actually, live our daily lives?
So metrology is the study of measurement. So without measurement, we wouldn't know, we wouldn't be able to communicate. We wouldn't know how much gas we were pumping at the gas station. We wouldn't be able to fly planes. We certainly wouldn't be able to go to the moon with SpaceX or several of those space exploring companies. It's a fundamental underpinning of measurements within the world. It enforces, validates, and verifies predefined standards, traceability, accuracy, reliability, precision. The global economy depends on reliable measurements and tests, which are, trusted internationally. We all have to trust our international partners that they're doing the same measurements that we are doing. No one's cheating each other. That's really what metrology is in a nutshell.
And
it's regulation.
I'll just jump off a little bit on what Chris said there. So you can think of it also, another way to say it is, it allows for measurements made in one country to be recognized in others. So let me just give you a real simple example. We all love our smartphones, and we expect that anytime we travel to any other country, we should be able to talk within that country or to somewhere else. That wouldn't happen without the specific standards that the cell phones rely on, but also it wouldn't happen without the measurements. So just to give you an example, there is a very well-known telecommunication company in Sweden who does most of their designs that end up being produced in as many as 30 countries around the world. And in their particular case, they mostly are making mobile base stations. But as it turns out, many countries, I've been to a number of their plants, for example, one in Brazil. So 2.5-hour drive outside of Rio de Janeiro, you get to a hilltop, and here's a factory that's producing base stations for use in Brazil. So that design came from Sweden, and the instruments that are being used are coming, the test procedures also from Sweden, but the instruments that are being used are coming from Keysight Technologies. And they have every expectation that the characterizations that they originally did in production test and the pilot testing in Sweden will result in the exact same measurements within appropriate measurement uncertainty interval in Brazil. And it turns out that across 30 different countries, they're able to achieve that.
I would assume that comes down to having, there's this concept of traceability where you can say everything leads back to this single source of truth. This, I love like the France kilogram situation where the kilogram used to be defined by an actual like sphere of metal, and now it's something different. But tracing back to an actual like pure source of truth that's repeatable and consistent and hopefully like infinitely accurate. Obviously not infinitely, but is that the case? Is that where that consistency comes from?
Yeah,
well, certainly. Go ahead, Chris.
Yeah, I mean, traceability is one of the key aspects of calibration and metrology. There's a number of SI units which are defined, and we trace all of our calibrations back to those SI units.
Okay.
Through an unbroken chain of traceability, and that's quite key. The unbroken chain. Because when we calibrate an instrument, we use other reference instruments, and then we use another more accurate reference instrument to calibrate our reference instrument, and so on and so on. So it's an unbroken chain back to these SI units.
So it's almost like a game of telephone from the source of the SI unit down to the power supply I have off the table here. I don't think that one's traceable, but assuming it were, then I could say this was traced or was calibrated by this other standard at the Keysight Calibration lab, which was then, in turn calibrated by something else that's, theoretically closer to the source or more accurate. Is that like that understanding?
For example, you have your power. Let's take your power supply. Let's say you set it to 5 volts DC. Then if you did that, then you would say, how do I know that's 5 volts? And the best way to initially check that would be to use some digital voltmeter. You might start with a handheld voltmeter. You might have a 3.5 digit, a 6 digit, whatever it might be. And then, of course, how accurate is the meter? Well, that's where calibration comes in. So if you then sent that meter into a a calibration lab, they would then measure that with a more accurate meter. For example, a Keysight 3455.
So you'd take that 3455, is that the right number?
58.
Yes. Mm-hmm.
Okay. And you'd take that into a cryo chamber where there is a Josephson junction, which is like this. It uses quantum physics basically to get a stable 5 volts or 10 volts. And
Right.
you get all the temperatures, settled, and it measures, and you say, okay, my 34, 55, or 58 is so, and we have like a way of knowing how good that 34, 55 is, like how accurate, how confident we are in that, maybe?
Well, so, we actually, in the case of DC volts, the most accurate standard I mentioned is a Josephson junction. Initially, that was developed by the National Bureau of Standards in the early 1980s. And the first company that had one of those primary standards, and outside of them, was HP in Loveland, Colorado. Really what you're doing is you're tracing your accuracy, because there are no perfect measurements.
So enlighten me, what is the official, so a production engineer would use accuracy. What would a metrologist use?
We would call it measurement uncertainties, and there's official definitions. There are documents called the official, the VIM, which I always forget the acronyms. I think it's Vocabulary for International Metrology.
Yeah.
But there are official definitions for these things. But the easiest way for the audience to understand is that if you were to imagine a statistical representation of all of the inaccuracies that could occur with any given measurement, then what you do is you have to take into account all of them. And when you do so, once you get to a standard deviation of what that is, that's what measurement uncertainty is.
Okay.
And the uncertainty changes based on what instrument you're using. The more accurate the instrument, one of the analogies I like to use is, if you're measuring something with a steel rule that's, from your garage, it's pretty inaccurate, but it's good enough for most applications. But for some applications, you need a laser interferometer, which is obviously one of the most accurate distance measuring tools. But obviously you wouldn't use that to measure from one end of your room to the other end if you're, putting a new carpet down or such. So it's, different instruments have different applications, but there's always a level of uncertainty associated to each instrument. And as we go through the traceability chain back to the National Measurement Institute, those levels of uncertainty get smaller and smaller.
Okay. Yeah, that makes sense. How do you actually?
So just to maybe review the fine point that I think Chris nicely made there at the end is what the international laboratories do, the NMIs or National Metrology Institutes, again, one of which is NIST in the United States. What their job is to maintain these national standards.
Okay.
They're the real geeks, the ones that work at the National Measurement Institutes. We're just like semi-geeks.
Okay. Yeah. There's always someone else, right? And they're like, oh yeah, those guys over in Europe or
Yeah, those are the ones that we can't even understand.
Fair enough. So how does this come back to, when I, for example, with the power supply, when I got my power supply, I got an envelope with a calibration certificate inside of it, and it had some numbers on there. What's the significance of that measurement uncertainty for, me on my bench or in a production environment?
Well, most likely you didn't get an indication of what the measurement uncertainty was of the final production test system. But if you just look at the flow of how instruments are produced, when you start out, you put components on boards or chips or whatever they might be. And then at a certain point, you turn the instrument on, and then you maybe close your eyes and hope that you don't see smoke. But once that instrument first turns on, now it's raw and it's ready to be adjusted. So then the next thing you do is instruments, whatever accuracy they have, is determined by the adjustments that are made. internally to that. And nowadays, almost every instrument, you don't find any of the any of the little screws that you used to use for variable resistors. Those have been gone for about 15, 20 years. And so now everything has circuits which can be controlled by microprocessors. And one of the main contributions by a measurement company like Keysight is the amount of effort that we put into the various adjustments. In fact, that is the most closely guarded intellectual property.
Interesting.
Right. Yeah. So we actually don't publish anything about the adjustments anymore because that's the sort of intellectual property that used to allow in earlier decades copying of instruments more easily. So it's very valuable intellectual property. And then if you look to the production line, we will adjust everything. And sometimes for our more complicated instruments, you will see entire automated lines which do automatic connections to many different instruments. And it might take as much as several days of automated measurements before that instrument gets to the end of the line. Now, at that point, it's operating theoretically as good as it can. And then when you get into the final test, that is an example of doing a calibration, because after all, calibration is simply measuring the current performance of the instrument. So a final test is just the first time the instrument is calibrated. And then, of course, you want and that verifies that, yes, it's meeting its specifications, and it gets shipped to the customer.
Okay. And then how does one go about deciding what sort of measurement uncertainty one needs? Like, do I need an 8.5 digit DMM, or is the 4.5 handheld behind me going to be good enough? Like, how do
that would be based on your application. I mean, many customers have different applications, different requirements. We have customers around the world that require the highest level of accuracy. We're talking 5G these days. We have 1 millimeter connector power sensors with very small uncertainties. If you're just using your digital multimeter to make some repairs on an oscilloscope that's broken or something like that, you don't really need anything that's overly accurate, because it's going to cost you more money, and the calibration is going to cost you more money. So it depends on the customer's application.
Well, Chris is so right there, and I'll just give another simple example. Now I'll give you a different example. One time I was visiting the U.S. Army's primary lab in Huntsville, Alabama, and they had 3458s in transit cases that were in because it turns out that on Apache helicopters, some of the sensors that they have are so accurate, and without going into the details of the systems, you don't want to send missiles to the wrong places. So they need a kind of accuracy that only a 3458 well calibrated can tell them what that is when they go to check that systems. And it's so important to them that they literally have mobile Josephson junctions that they send around to forward locations to make sure that the 3458s are absolutely operating. So it just depends on the application, but it when it's critical, people take the care.
So I didn't prep this question with you, but do you have an example, either of you, of like the most overkill example of metrology that you've seen? But is there a situation that sticks out for you that was like, that was cool, we went overboard, but we did it?
I have one. Since we're talking about one of the most accurate voltmeters in the world, I know a number of defense contractors who like to use 3458s in their laboratory, and I have often said to them, "Why would you do that? You don't need anywhere near that accuracy. You can absolutely you wouldn't even need to do a measurement uncertainty analysis. It's so accurate." And they go, "You're starting to get it, kid." They don't. If you bring in something that accurate, then they don't have to do an error analysis.
Yeah, that makes sense. It's just so beyond what they need that they don't even have to worry about it.
Don't even have to worry about it. And I think that's pretty smart. I would do it too.
Yeah.
Chris,
yeah.
you
when you can.
You sounded like you might have had something there.
Yeah, I mean, there's always lots of these overkills. One of the times that I see it is in our own service centres. We like to have the most accurate equipment we can in our automated systems. Now, we might be running through a piece of equipment that nowhere near needs the accuracy in the setup that we've got, but we like to keep it that way because it gives us some fallback. We know then that we're giving our customers, or we're giving the customers the best accurate measurements we can, even if the report that they get is the level of uncertainty is larger than for some other instruments. But yeah, so we like to make sure that we're delivering the best of the best.
Yeah, that makes sense for sure. How do you go about describing accuracy? It may not be as simple as or uncertain. I said accuracy. Look at me. I'm doing it wrong. I could see on your face. It's just like the disappointment. Just kidding. How do you go about? It's not necessarily just like, oh, your measurement uncertainty is good, or oh, it's bad. Like there's got to be. Is it percentages or numbers or millivolt RMS values or?
Well, certainly there are. There's a quantity that's called test uncertainty ratio, which is a fraction. And that if you are going for a certain spec, let's say you have 1 dB accuracy that you're looking for, and let's say that your measurement uncertainty, your expanded measurement uncertainty, so I've introduced another term. Most of the time, measurement uncertainty, it's a statistical quantity, obviously. It's a standard deviation. Most of the time, it has a Gaussian curve, which means that if you have plus or minus 2 standard deviations, you then have a 95% coverage interval where that's likely to be. So one of the figures of merit is a test uncertainty ratio, where you divide the spec by the expanded uncertainty. And let's say that you had, let's say that expanded uncertainty was 0.25 dB. Now, some of the really sharp people in the audience might know that you're supposed to convert to linear, but we're just going to go quick here for the time being. If you took 1 dB divided by a quarter, that's a ratio of 4. Generally speaking, anytime that you can have a ratio of 4 to 1 or higher, that's pretty good metrology.
So if I have someone new in my lab, it's an intern or a first-year person or someone who's never worked with this before, how do I kind of describe to them the importance of metrology and how to quantify it?
That's a great question. Sometimes when I talk with various marketing or salespeople, they go, oh, I know, let's call it high, medium, and low. And you go, great. So what does high mean? What does low mean? But what I find is if you can get to percent risk, then just about any person can understand that. And if you look on, everybody has a weather app on their smartphone. And certainly when you think, I'm going to take my family to the beach or to the lake, whatever it might be, that is once we're allowed to, then you probably would glance at your phone and say, okay, if we're going to have a picnic, what's the chance it's going to rain?
Yeah, like for me, so I have some mountain biking trails, right that way. If it says 60% chance of rain and I want to bike, I might take that risk because I can just get home right away. The consequences are low, but I'm not going to drive up an hour to Denver somewhere to ride because have it rain on me because I have to drive all the way back. There's a lot more consequence.
Exactly. Good case in point.
Yeah.
Cool. And you guys have actually authored some papers and some specs on this topic. Is that right?
We have. You almost want to ask yourself, why do people make measurements in the first place? And so whenever you take a measurement and you compare it to a specification, you're making a pass or fail decision. And so that was the whole point of making the measurement. There are no perfect measurements. So this is shocking to a lot of people. There are no perfect measurements. As beautiful as our instruments are with all those wonderful digits, that isn't the true answer. Only the Supreme Being knows what the true answer is. All we can do is say, this is what we measured. and here's how accurate we believe that measurement to be, which is, of course, measurement uncertainty. Now, once you have the measurement uncertainty and you decide to do a pass or fail decision, then the question becomes, there is a risk. So just because there are no perfect measurements, it means that when you say it passed, it didn't always pass. There is some false accept risk. Or if you fail something, there's some false reject risk. And so then we go back to before. What you'd really like to know is what percent are we talking about? And it turns out that one of my colleagues, John Harbin, who's the chief metrologist for Keysight, and I have written about this in several papers at NCSL, and there's a Keysight application note, which if you go to www.keysight.com/find, these are backslashes, /find, all one word, decision rules. We have a very nice 5-6 page note where you can take a look at any calibration report where you got the uncertainties from a Keysight instrument, and in just less than a minute, you can look at a couple of tables and figures and estimate for a given measurement what was the percent likely risk of false accept, or if we failed it, false reject. So we give that to you so that people can make their own decisions.
Great. And we'll put a link for that app note in the description of this video and on the webpage, eestalktech.com. So those will be in the show notes as well. Decision rule. That's actually a pretty well-respected app note in the metrology industry. So go check it out if it's something you're interested in. Yeah. So Chris, what was it like coming out of the government, application industry over into the private sector? How did that metrology mindset change?
Yeah, I mean, in the military sector, you often, you have 3 different parts, or sometimes 4 different parts of the military sector: the Army, the Navy, the RAF. They all look at metrology in a different way. The Army just like to go and shoot guns, and if it shoots, it's great. If it doesn't, well, okay. The Navy, very much deal with communications, big guns as well, very high accuracy systems. So they're the kind of the medium level. And the Air Force are very worried about planes falling out of the sky. So they have a very high requirement for accuracy and for small uncertainty. So what you usually find in the military is there's 3 different applications. But when you come over to Keysight, you have many more applications. You have hundreds, if not thousands, of customers, and they all have different requirements. They all have different levels of expectation as well. In many commercial companies, they are there to make some money, obviously, but they obviously want to give the best service. The best quality, which is something that everyone strives for, but in the commercial industry, it's a very different animal. The pace of delivery is a little slower at certain times, but at certain times when there's perhaps a war footing, things change quite dramatically. And there can be several instances. I've seen several instances of things going wrong in the military. And I've actually seen plane fall out of the sky. But in the commercial side, there's a bit more of an aspect to quality and ensuring the quality of the product that goes out the door is as good as it can be.
Okay. Yeah.
Could I add something from the commercial standpoint? So Chris was just reminding me. In the Keysight world, what we do is, I won't use the official Vim definition because it's really best used as to put you to sleep. But what we like to say is that we measure the current performance for every corresponding to every published spec every time you send it to us. So current performance accurately measured every spec every time. That's the Keysight line in the sand, and we call that a Keysight calibration. So there are other companies that say, oh, we do the same as Keysight, except for they're using 30-year-old equipment. If you're using 30-year-old equipment, the likelihood that it's more accurate than what you're testing is extremely small, okay? So that's one sin. that's oftentimes committed. But the biggest sin is that, for example, the planes falling out of the sky that Chris just mentioned. One of the things that you really have to watch out for is phase noise on your warding receivers in case something's being shot up at you. And that's a very tricky measurement to make, and it takes a lot of very expensive equipment. If an instrument has a spec for phase noise, we measure it every time. A lot of other service organizations would tell their customers, no, that's just a design characteristic. You don't need to check it. And what we find is mostly you don't need to check it except when it changes. So if you have a jet in that's in for service, the reason the military checks it is because sometimes it changes. So we have a line in the sand of measuring every service, but some customers who want lower risk say, you know what, I'd like to not only know that you measured everything, but I'd like to know what were the actual measurement uncertainties that you have. So we have another service called Keysight Cal plus uncertainties. That's a little bit more expensive, but if you purchase that service, then you have an actual record of what were the measurement uncertainties for that calibration, and you can then look to that app note and make estimates of percent risk. And finally, we have our very sharpest customers who understand this the most. They say, you know what, we understand risk and we want to keep it as low as possible. Therefore, we want the instrument to behave as closely as when it was first shipped to us as we can. So therefore, we would like you to test not only to the specification, but to a guard-banded specification. And so for those people that are aware of doing that, we then have Keysight Cal plus uncertainties plus guard banding, where we guard band by the amount of the expanded measurement uncertainty. And in those cases, once that comes back with clear passes, they can then be absolutely much more confident to a very small risk percentage that the instrument, when they use it to make a pass-fail decision, is correct.
So we're out of time for today. Bob and Chris, thank you so much for your time, and I loved tapping your expertise. And I would say that people will love it, but there's probably some measurement uncertainty with that. So people will probably love this podcast. I kind of picture your boss like, oh, are you going to get this done? It's like, well, yeah, probably. It's like, it's not a yes or no. There's no perfect worker.
No.
But it's been a real pleasure.
He's getting it.
Yeah, it's been a real pleasure having you guys. Thank you so much for your time. This was also super short notice, so I appreciate you jumping in with less than 24 hours notice, literally, to get you guys here. So thank you. I'm Daniel Bogdanoff, and again, Chris and Bob, thank you so much for coming out.
Thank you. Bye.
Thank you for watching and listening. Make sure to subscribe to Double E's Talk Tech in your favorite podcast engine or over on the Keysight Podcast YouTube channel. We also have some new podcasts coming out down the road that are outside of Double E's Talk Tech, so the YouTube channel is a great place to see all of those together. Also, check out our sister channel, Keysight Labs, and make sure to check out Keysight University using the link on the webpage or in the show notes. And that's it. I'm Daniel Bogdanoff. Thanks for listening. I'll see you next time. Or hear you next time, or you'll hear me next time, or however that works.